We are seeing the subject Cyber Physical Systems Framework. In this video, we'll see the basic architecture of a control system along with two examples. This is the architecture of a control system. Here we are having a plant that is to be controlled, and this plant can be controlled by a controller. This controller will control the plant through a device called actuator, and this plant will be monitored by a sensor, and the monitored data is sent to the controller to make some decisions. This is a basic architecture of a control system that has four parts: a plant or a system that has to be controlled, and we have a sensor to monitor the plant and to collect real-time data, and the data will be given to the controller to make decisions. The controller will be taking some reference inputs, maybe by manual or by automation. It has some reference inputs, and based upon the reference input and the real-time data collected by the sensor about the plant, the controller will make some control actions, and this control action will be given to the plant through the actuator. Will be given converted The control signals will be converted into a form that can be actually understandable by the plant. So along with this control signal, plant will also receive some disturbance that cannot be predicted earlier. So this is out of the control of the controller. So this plant that has to be controlled by the controller will be receiving a real-time data from the sensor, and based upon the sensor data and the reference data given by the human or automation, the controller will make some decisions, and the decision controls will be given to the plant. Even though we are having a control over this feedback loop, this disturbance is out of control of a controller. This will lead the plant output to deviate from the expected output. So the physical world that is to be controlled is modeled by a component called the plant. That's what we have seen. The evaluation of the plant can be influenced by the controller using actuator, but not only upon this actuated signal, the plant will also receive the uncontrollable signal that is called as disturbance from the environment. The controller responds to the commands from the user called reference inputs and can make decisions based on the measurements of the plant provided by the sensors. That's what we have seen. Let us see one example called heat flow. This is a heat flow component. The component name is net heat. So this component is going to have two inputs. One is called H plus, other one is called as H minus, and this component has only one output called H net. This component doesn't have any internal state, so this is stateless component. The component is stateless. It has two input variables H plus and H minus and one output variable called H net. This denotes the heat inflow. H plus denotes the heat inflow, H minus denotes the outflow of the heat, and H net defines the net heat flow. This is the two input signals and one output signal. So this component calculates the difference between the inflow and outflow and gives that as an output named net heat flow called H net. So now we are going to convert these into signals. So we already know that when I want to represent a variable as a signal form, I have to mention a bar over that. Let us see that. So for the input variable H plus, we have a signal called H plus bar. Given a signal H plus bar for the input signal H plus. And similarly, we have another input signal called H minus. So I should have a signal called H minus bar. H minus bar is a signal for the input variable H minus. And we have an output variable called H net. So I have a signal called H net minus bar. So these three are the signals corresponding to the three variables, two input variable h plus and h minus, one output variable called h net. The value of this is equal to difference between these two components. H net of t is equal to h plus of t minus of h minus of t. This is applicable for any time in t, that is for all time t. So this H net of t is the output signal. This signal is called as response of the component. So any component we call the output as response in continuous terms. So if the input signals are continuous, then output signal is also continuous. If the input signals is discrete, output signals will also be discrete in nature. So here we have a continuous input. So because of continuous inputs, we have continuous output. This is one example. Now we'll see another example called motion of a car. We have a car here, and this car is having a force applied in this direction. The applied force is F. Because of the applied force, this car is moving with the velocity v, and it is displacing a position called x. So whenever we have a force, we have some opposing force, we call it as friction, that is equal to k into v, where k is the coefficient of friction and v is the velocity. Now we are going to model this car as a component that is having input f and output v, velocity v. So now we have two state variables, one is called x, other one is called as v. So this x is having a limit, so it is parameterized with the level called xl to xu, low value of x and upper value of x. So v should have a low value velocity vl and then upper limit, lower limit, upper limit for the variable v is vl and vv. Similarly, lower limit and upper limit for the variable x is xl and xu. So this is the two variables, and we have, based upon the current value of x and v, we will calculate the next value of x and v. We call it as x dash and v dash, and the value of that is equal to x dot is equal to v and v dot is equal to f minus kv by m. So how we got these two equations? That this is very easy for us. We know this already. So these two equations are already known to us. We have the standard notations and representations. We know about this. So when we have a distance x, and we know how to represent the rate of change of x, we represent this by the term dx by dt. So dx by dt is called as rate of change of distance. We call it as velocity v. So when I differentiate this again, that is, we will be having a term called d square x by dt square. This is rate of change of velocity, that is dv by dt. So this is the term that is already we know about this. When we have a distance x, a dx by dt, first derivative of x is called as velocity v, and this velocity v, so rate of change of distance in our continuous time model, I call it as x dot, first derivative of x. And we have second derivative of x, that is d square x by dt square. I can call it as x double dot, second derivative of x. We have to place two dots over here, and then I call that is second derivative of x means d square x by dt square. That can also be called as differentiation of velocity, dv by dt. So I can represent it by the term called v dot, single dot I can keep. So we have our standard Newton's law. We have F is equal to, when we have the value F is equal to m into A, F is the net force that I have and m is the mass of the element, A is called as acceleration of this. So we have F here only applied force. Now we have here applied force as well as friction. So the net force what I have here is applied force minus of opposing friction. So I have minus of kV opposing. This is equal to m into A. M is mass, let the mass be as such. A is called acceleration. So instead of acceleration, what I have to represent is V dot. So let me mention it as V dot. So from this equation, I can easily write F minus of kV totally divided by m is equal to my V dot. And already we have written our x dot is equal to V. So we have our two equations. Our first equation is x dot is equal to V, and our second equation is V dot is equal to F minus kV divided by m. So these are the two equations that we got for our motion of the car component. I hope this is clear for you. So this K represents the friction coefficient, M represents the mass of the car, and the quantity x dot denotes the first order time derivative of the signal, and that is called as velocity of the car, and x double dot represents the second order derivative of the signal, that is acceleration of the car. Thank you all. In this video, we have seen the architecture of the control system along with two examples of continuous time models. We'll see remaining in our next video.